All right, hello. So this is our last lecture with content. There's going to be one more lecture after this where I go through kind of a practice final exam, but that'll be it. All right, so today we're going to talk about approximating integrals. So this is kind of our last lecture in the this little series about an introduction to calculus. So the two main tools used in calculus are the derivative and integral. So we talked about derivative last time. We're going to talk about the integral this time. All right, so what are integrals? Integrals calculate the area between a function f of x and the x-axis. Okay, so let's say that we have some function. So in this particular case, I'm going to graph the e to the x function. All right, so f of x equals e to the x. Yeah, I think we haven't really talked too much about e to the x. Let's call it 2 to the x, something like this. All right. This is our exponential function. Okay. And let's say that we want the area for this thing between 1 and 4. So here's 1, and let's say this is 4. Okay. So the area under the graph would be the area between the function and the x-axis, right? So it would be all of this area right here. All right, so the integral calculates that area. Okay, so the area, the notation for the integral looks something like this. It's kind of like a kind of an S shape. And you put the endpoints 1 to 4 of f of x dx. And if you want, you could make this f of x even more specific. 1 to 4 of 2 to the x dx, or whatever actual function it is. Okay, so the two things are these endpoints. So this is what's called the upper endpoint, and this is called the lower endpoint. And that tells you basically when you start calculating the area and when you stop calculating the area. So it's these two endpoints tell you which region you're actually calculating the area for. All right, so one of the things you might be wondering is why do we need to calculate areas? Well, from a mathematical standpoint, integrals are useful for calculating weird shapes. Right, so we're okay with calculating, the area of rectangles, the area of, triangles, things like that. But you can have all kinds of weird shapes. So, like for example, this one, it has 3 straight sides, but then it's got this kind of weird curved side. And so, when you need to calculate the area of a weird shape, that's really where integrals come into play. And in addition, like in terms of applications, engineering, physics are the things I'm most familiar with. They're useful for calculating the accumulation of changes, especially nonlinear changes. And nonlinear just means that basically you have these kind of curved portions of the shape. All right. So an example I can think of is, let's say you wanted to calculate the force of the water on a dam. Basically, what happens is that toward the bottom you have a higher pressure, and toward the top you have less pressure. And so what you would do is you would integrate over the height. So instead of dx, it would be dh or something like that, of those pressures, and you're sort of adding up the force due to each of those layers of water, and that's kind of what integrals are really good for. So they're good at calculating those kind of changes. So in that case, I guess that's a that would actually be a linear change, but you know, whatever. It's a calculation of just accumulation of things. So like accumulation of those forces of those different layers of water. But it's used for all kinds of things. I think when you start getting into this, where you start using it a lot, it just becomes kind of a general concept of just calculating values of things over surfaces or areas or over other variables, etc. All right, so it's a very kind of useful tool in a lot of areas of science. All right, so basically just like we did before, we're going to, for the derivatives, we have a strategy for approximating integrals. Okay, and basically our approximation is basically we're going to approximate the area as close to the area of a group of rectangles. Right? Why rectangles? Because we know how to calculate the area of rectangles, right? You have some base, you have some height, and the area is equal to base times height. So we know how to calculate the area of rectangles. So what we're going to do is we're going to approximate, things that have weird shapes as just a series of rectangles that we can easily calculate. All right, so the example that we're going to do, I'm going to go through in much more detail, is this semicircle equation. So this semicircle will look something like this. So it has a radius 4, and the equation for this is f of x equals square root of 16 minus x squared. Okay, so that's the equation for this. So there's no plus or minus here, and the reason is because we're only looking at the positive values, which is the top half of the circle. So we have the semicircle, and we want to figure out is the area of from 0 to 4. Okay, so we have 0 to 4, and we want this area right here. All right, so it's a curved shape. There's actually a way that you could do this without doing an integral, and we'll talk about that at the end. But that's what we want to approximate. So what we're going to do is we're going to approximate this as a series of rectangles. And what that looks like is it's going to look something like this. So our first approximation is we're going to approximate this rectangle, this circular part from 0 to 4, as kind of a rectangle that looks something like this. So obviously, that's not like a great. That's not a great approximation. It kind of, you get a lot of area that you don't really want, but that's our first approximation. So this width right here of this rectangle we're going to call delta x, and delta x you can think of as the distance, which is 4, divided by how many pieces you have, and so we're breaking it up into one piece, so that's equal to 4. All right. So that's our first approximation. Then we're going to do a series of better approximations. All right, I'm not doing a great job drawing this thing, but hopefully that's okay. So what we're going to do is we're going to approximate this then as 2 rectangles. So a rectangle that looks like this, and then a rectangle that looks like this. So this one, it might be hard to see, but this one's a little bit bigger than this one. And again, in this case, we're going to use a delta x. But our delta x is the distance. 4 is going to be broken up into 2 rectangles, 2 pieces. And so our delta x is 2. And so this is going to be a little bit better than this. And then we're going to approximate again. And this time, we're going to approximate it into 4 rectangles. So this first one looks like this. And the second one looks like this. Those two will be very close looking. And this one's a little bit shorter. And this one's a little bit shorter, right? So delta x is even smaller. So delta x is equal to 4, and then we divide it into 4 pieces, so delta x is 1. So the width of each of those is 1. And you can see if we started to increase this even more, sort of ran out of space here, but what you can imagine is we could make delta x extremely small. Right, so we could take this and we could make these like little thin slices, right? So really small. And basically the smaller we make these slices, smaller we make delta x, the better the approximation is going to be. So as we go toward like smaller and smaller rectangles, basically it's just going to get better and better. And so the way we're going to write this is if you took let's say 4 and you broke it up into n pieces, then it would be 4 divided by n. And what we're going to say is that we're going to try to break it up into like a lot of pieces, because that's when it becomes really good. So we're going to write this as the limit as n goes to infinity. So infinity is like a huge number. So this n is a lot of pieces. So we break this distance 0 to 4 into an infinite number of pieces. It's going to be like a perfect match for the original. So that's kind of how this approximation works. You start off with one rectangle, 2, 4, you work your way up, and you get closer and closer to the actual area which has this curved side. And that's basically our strategy that we're going to do to try this out. Okay. I don't know if you can see this too well. I'm just going to rewrite this a little bit bigger. So this is the limit as n goes to infinity of 4 divided by n. Okay. All right. So let's actually do it. There's one other thing I need to talk about first, which is that there are two ways of drawing rectangles. Okay, I should have used black there. In fact, there are more than this, but for our purposes, we're just going to talk about two. And the two methods are what are called the left endpoint approximation. And here, I'll draw a line here. And the right endpoint approximation. Okay, so let's say that we have some curve like this, and we're drawing a rectangle, and we want to draw this rectangle with a delta x of 1, right? So delta x is equal to 1. So when we extend these lines up, we have two choices for how to draw a rectangle. We can either use the height as the value on the right side or the left side. So in this case, we're going to use the value on the right side. So this point right here is called the left endpoint. All right, so that's actually one word, but that's what I fit there. So that's the left endpoint. But you could think of the same thing. So if I'm going to try to reproduce this picture. If you think of it the same way, you could draw a rectangle, but instead of going to that left endpoint, you could go to the right endpoint. Okay, and this point right here is called the right endpoint. Okay, so in this case, the height of this function, of this rectangle, is going to be equal to the function evaluated at x equals 1. So this is f of 1. And f of 1 means the y value at x equals 1. All right, and the height here is going to be f of 2, because on the right hand side that's where the 2 is, and this f of 2 is the y value at x equals 2. Okay, so the area we know is just the base times the height, right? Which in this case it's going to be the base is just delta x. So I'm going to put this in front, and the height is f of 1. All right, so that's going to be our equation for the area. And the area here is also just base times height. It's this dimensions of this rectangle, right? So it has, this rectangle has delta x as its base and has a height of f of 1. And this one, this kind of smaller rectangle, has a base delta x and a height f of 2. So our area here is the same idea. It's going to be f of 2 times delta x. All right. Obviously, this rectangle is bigger than this one. So what ends up happening here is when we do this left endpoint approximation for this particular function, we're going to be calculating too much area. All right. And for this one, our rectangle is smaller than the curve, so we're going to be calculating too little area. All right. So what we're going to do is we're going to use both methods. We're going to use a left endpoint to draw these bigger triangles, and this right endpoint to draw these smaller rectangles, bigger rectangles and smaller rectangles. And what that's going to help us do is it's going to help us create an upper and lower limit. Okay. And what that's going to allow us to do is kind of like go into. So if I were to say, like, guess a number between 1 and 100. Okay. So if your first guess was, say, 50, I would say, it's higher than 50. A good strategy would not to do something like, you shouldn't say, is it 51? Because that doesn't really help you too much. You would say maybe like 75. And if I said lower, then that would give you kind of a range, 50 to 75. That's kind of the strategy we're going to do here, which is that we're going to use this method, which is we know is going to be bigger, and we're going to use this method, which we know is going to be smaller. And that would kind of give us kind of a range of where the actual area is. And as these approximations get better, these two numbers, this upper and lower limit, should get closer and closer together, and they should converge on the actual answer, which is what our strategy is going to be. Okay, so that's what we're going to do. So let's do it. Having some problems with this paper. Okay. All right, so let's do approximation 1. So for approximation 1, we're going to use one rectangle with delta x is equal to 4. All right, so the width is the full width of the area that we're looking for. Okay, so we're going to do the two sides. So we're going to do the left end approximation, which I'm going to call LEA. And then we're going to do the right end approximation, which I'm going to call REA. Okay, so let's draw our functions here. Oh yeah, also our function f of x is the square root of 16 minus x squared. All right. All right, so we have our function that looks something like this. All right, so the left end approximation is we use this range. We're going to use this side right here, so that is going to be our rectangle. On this side, this is kind of weird. If we look at this, this rectangle has no height. So our rectangle is actually just kind of a flat portion of the line, which is kind of weird. And you'll see that on these other ones, that's not the case. But for this one, that is happens to be what it is. All right. So here, the area is going to be equal to the height, which in this case is f of 0. It's the y value at this times the width delta x. All right. So f of 0 is going to be, we just have to plug that in. So it's 16 minus 0 squared. And delta x is 4. So this is the square root of 16, which is just 4 times 4. So the area is 16. All right. Now in this area, it's f of 4, which happens to be 0. But I'm just going to kind of go through this just so that we see how this works. So it would be 16 minus 4 squared. That's evaluating the function at x equals 4 times 4. And this is just 0 times 4, which is just 0. All right, so that's not a great approximation, but it gives us, this is just the first approximation, so it's not that great, but it gives us kind of an upper and lower bound. So what we know is we know that the area is greater, area is less than 16, and we know the area is greater than 0. So way you could write this is it's 0 is less than area. No, 0 is less than the area, which is less than 16. So we've put a bound that our area has to be somewhere between 0 and 16. We'd like a better one, and that's basically why we're going to do additional approximations. But that's our strategies. We're going to do left end and right end, and we'll get kind of a limit, and these two upper and lower bounds should move closer together. All right, now I'm ready for this paper. Let's do approximation 2. Okay, so for approximation 2, we're going to use two rectangles, and we're going to use delta x is 2. And just to remind you, our f of x is square root of 16 minus x squared. So we're going to have the left end approximation, and we're going to do the right end approximation. We're going to draw our functions. Okay, and we're going to break this up into two. So our first one, our left-hand approximation, is going to look something like this. So where it touches here, that's the height. So we have two rectangles there. And this time I'm going to start from the right-hand side. So you can see that I'm inside this function. And this is our other one, so we just get kind of a little 0 flat piece. But technically that's two rectangles. It's just a rectangle with 0 height. So that's kind of weird. But that is basically what we're trying to do here. Okay? So if we look at these rectangles, all right, they have width delta x is equal to 2. All right, delta x is equal to 2. So the area, in this case, is the area of each of these rectangles added together. So this first rectangle has a height, f of 0, that's its y value right here, times delta x. And the second rectangle has a height, f of 2, times delta x. Okay? So I think actually it probably is going to be helpful, and we'll see this a little bit later. I'm going to calculate f of 0, which is the square root of 16 minus 0 squared, which is 4, and f of 1, which is square root of 16 minus 1 squared. Oh, I'm sorry. Yeah, I'm sorry. This is f of 2. That's why I was looking at my notes and I was like, I don't remember that number. All right, yeah, so that 16 minus 4 is 12, so this is square root of 12. Square root of 12. All right, so if we plug those in, we get 4 times 2. Delta x is 2. F of 2 is square root of 12 times 2. And we can put that in our calculator and see what we get here. All right. All right, is there a way I can see this clearly? That's probably the best we're going to do. So 4 times 2 plus square root of 12 times 2. And I get 14.92 or 93 as the area. So again, that's going to be too big because we have some of this rectangles outside of the curve, but that's an upper limit. And then for these, we have an area, which we're going to use the right-hand side. So f of 2 times delta x, which is this rectangle. And then we're going to have plus f of 4 times delta x. We know f of 4 is square root of 16 minus 4 squared, which is just 0. So f of 2 we already calculated is square root of 12 times 2 plus 0 times 2. And we're going to calculate that number as well. So that would be square root of 12 times 2 plus 0 is 6.92. Or 6.93, I'm sorry. Because it's this 8, we're just going to round that to 6.93. So from that, we have a new upper and lower limit. So we know that 6.93 is less than the area, but the area is also less than 14.93. So what happens is our endpoints are getting closer together. Before it was 16 and 0. So we're getting closer together with this approximation. And we're going to do one more approximation, just to see that it's getting closer and closer. So this one is called approximation 3. All right, so for this one, we're going to use four rectangles. And we're going to use a delta x is 1. And again, the function is square root of 16 minus x squared. All right, so we have the left end approximation and the right end approximation. And we're going to graph our functions. All right, my circles are getting worse and worse. Okay, so for this one, we're going to have 0, 4, 2, 1, 3, 4, 0, 2, 1, 3. There we go. All right, so we're gonna graph our rectangles based on this picture. So here we're gonna start here. It's our first rectangle. So that is our left end approximation. I'm using the left end of the triangles to establish the heights of the rectangles. I keep saying triangles. And then this one I'm going to use the right end of the triangle, right end of the rectangle to establish the height. Okay. And this one, again, this is going to have, that's like kind of a fourth rectangle with height 0. Okay, so in this case, the area, we're going to use the left end, so that's at f of 0, f of 1, f of 2, f of 3. So our area will be equal to f of 0 times delta x plus f of 1 times delta x plus f of 2, which is this one has a height f of 2. This last one, f of 3 times delta x. So you notice that I'm evaluating the function at just the left end of each of those rectangles. Okay? So we need to calculate all of these things. I'll show you how to do that in a second. And then here, we're going to use a right end. So this one is f of 1 because it's evaluated at this right end. Okay. All right. So we need to evaluate a lot of these. So let's do that. So I'm going to show you a way of doing this in your calculator, which is kind of a shortcut way of doing this, especially if you have this TI calculator. It's kind of an easier way of doing this. But basically what you can do, so there are other ways you could do this, but what I'm going to do is I'm going to write this equation in my calculator, square root of 16 minus, and then I'm going to do this first one, 0 squared. All right, I don't know if you can see that. All right, so that is my f of 0 is 4. And then if I want f of 1, what I can do on this calculator is I can just press the up arrow, and that'll allow me to change this value. So I'm going to change the 0 to a 1. So x equals 1 now. And I get f of 1 is 3.87. And then f of 2, I'm just going to press up and change this 1 into a 2. 3.46. So if you're really careful, you could actually, keep these in your calculator or write it as the radical version, which would be kind of a more precise value. So I'm going to replace 2 with 3 here. Get 2.65. So when you round this thing, that leads to a little bit of an error, but that's okay. All right, so the area is going to be f of 0, which is 4 times delta x, in this case is just 1, plus 3.87 times 1 plus 3.46 times 1 plus 2.65 times 1. And when you do all of that, the area you get is 4 times 1 this way is probably easier. 4 times 1 plus 3.87 times 1 plus 3.46 times 1 plus 2.65 times 1. You don't have to do these times 1s, but you can hopefully get the idea. So you get 13 point, all right. Oh, I'm looking at the wrong sheet here. I get 13.98, and that is what I got on my notes. Okay. Okay. And then this one is the same deal. The only one that we didn't calculate is f of 4, but f of 4 we know is 0. Right? So you can do the same thing. So f of 1 is 3.87 times 1. F of 2 is 3.46 times 1. F of 3 is 2.65 times 1. And then f of 4 is 0 times 1. So the area, if we calculate all of these, 3.87 times 1 plus 3.46 times 1 plus 2.65 times 1 is 9.98. And that's what I got in my notes. Okay. So we know our upper and lower bounds are getting more and more accurate. So we know that 9.98 is less than the area, which is less than 13.98. Okay. So in your homework, you're going to do something like this. What you could do, Here, I'll do this in red here. You could do better approximations. And you could get those limits to get even closer together. So you could use like delta x is, 0. Half, or 0.1, or 0.01, or 0.001. Whatever it is. You can get smaller and smaller, and you'll get a better and better approximation. But obviously, it's just going to be harder to do. So there are mathematical tricks. If you take calculus, you'll learn about convergent series and things like that, which allow you to do these calculations a little bit easier. All right, but you get better approximations for the smaller you go, but it just takes more and more work. All right, so let's do a summary of our values. So we're going to do kind of the width, which is our delta x values, as our first row. And then we're going to do the left end approximation as our second row. And then we're going to do the right end approximation as our third row. Okay, so the values that we had our first approximation was 4. And when we did that approximation, let me just look back here, our left end was our left end was 16 and our right end was 0, so it was somewhere between 16 and 0. And then we went to a better approximation where we used a width of 2 with 2 rectangles. So this is how wide they were, not how many rectangles there were. So this was, here, let me put a note somewhere. So this is 1 rectangle, and this was 2 rectangles that are width 2. And when we did 2 rectangles, we got a value that was 14.93 and 6.93. So you can see those upper and lower limits got closer together. And then we did a width of 1, which was 4 rectangles. And that's the one we just did. And when we did that, we got an upper limit of 13.98 and a lower limit of 9.98. So you can see that they are getting closer together, but still, I don't know, you might not be too satisfied with a gap of, that'd be about 4 units wide. So the answer is somewhere in that 4-unit gap between those two values. So what I did is I actually solved for this. So imagine that you were to take this to like, an infinite number of rectangles, where delta x, here, let me write it as, I'll write it as red. Delta x is equal to 4 was the width of the area we're looking for, divided by n, but the limit as n goes to infinity. So we do infinite number of rectangles and we break it up into like a super tiny little amount. So if you were to do that, these two ends would converge toward this value 12.56. So these upper and lower bounds would kind of approach each other until they gave you this value. So on your homework, you basically go through this process with a different function. That function is, I think it's like 1/20 x plus 5 squared. But you basically go through the same process where you approximate the area using different rectangles, number of rectangles, in the left end approximation and the right end approximation. So I want to show you, so you should have enough to do this homework. I just want to show you one thing, which is how I calculate 12.56. So there are two ways. There's like a geometric way. So basically the geometric way is, one of the things you realize is that the area that we're looking for is basically like 1/4 of a circle. So maybe you were noticed this in the beginning and said, I know what the area of a circle is, and I know how to calculate 1/4 of a circle. But the area of a circle is just pi r squared, where r is equal to 4 units. So our area of this shaded region would just be 1/4 times the area of the total circle, which is pi times 4 squared. And if you do that, you can cancel out this, but this happens to be 4 pi, which is, if you calculate, 12.56. All right. So that's the way you could do. There's no, you don't even need calculus for this particular answer. But if you just did, here, I'll just do 1/4 times pi times 4 squared. You get 12.57. I could have rounded it to, but that's basically what it is. So that is how you could do it. If you take calculus, you'll learn more advanced methods for solving these kinds of integrals, and so I went through some of that to kind of give you an idea of what that might look like. I'm not sure what this is, probably like more calculus 2 kind of stuff, but this is basically the work that we would do. You're probably not going to understand that. That's okay. But basically the idea behind this, and the reason I went through this is because, to be honest with you, I looked at this and I was like, I don't remember how to do this integral. So I did a little bit of research and I was able to kind of figure it out. I remembered some things. But basically you change this integral from a function of x to a function of theta, and you replace this is called the integration variable, from dx to the theta. So you relate x to theta, which is just like, since it's a circle, you can inscribe a right triangle inside of it. And x is 4 cosine theta, radius times cosine theta. That's basically the x component. And then x squared is this, theta equals this, and you have to change your endpoint from 0 and 4 to pi over 2 and 0, and you have to change your integration variable dx to this quantity, -4 sine theta d theta. So you have to be able, so one of the things about doing this is that you have to know how to take the derivative of cosine theta. But you replace that, so it's only a function of theta. You factor stuff out, you combine stuff. You get this, and you have to use a trig identity, which is sine theta squared plus cosine squared theta is equal to 1. So 1 minus cosine squared theta is equal, square root of 1 minus cosine squared theta is sine theta. And then you get sine theta times sine theta, which is sine squared theta. Then you have to use this half angle trig identity. Cosine 2 theta is this. So sine squared theta is equal to this. And you get 2 integrals. You have to do 2 integrals. There are rules for doing integrals. You do this first one, which is 1. Second one is cosine 2 theta. So this one is just theta. This one happens to be half sine 2 theta. And then you evaluate the endpoints. The second term turns out to be 0. You get -8 times -pi over 2, which is 4 pi, which is 12.56. So you get the same answer. This is something, if you take more calculus, this is the kind of thing that you'd start getting into. All right, so that was our last content. Hopefully you got an idea of what calculus is, what it's like, and maybe what you'd be getting into if you took it. I think calculus is a really cool subject. If you really get into it, you'll enjoy it. But it's not an easy course. And if you want to talk more about it, if you want to have some questions about calculus, I'd be happy to talk to you. Just send me an email. All right, so I hope you're safe. I hope you're doing well, and I'll talk to you next time. Bye.